I get this random message from Noah I had forgotten about earlier. He goes, are we still meeting the Sambo champion tonight? I guess Sambo is like a martial art, right? Yeah, I think it's a kind of martial art. So I figured, well, okay, sure. I have to fight the guy. I'm down. I just want to know what I'm getting into so I can come prepared. So hopefully we'll have some video footage. Should make it fun. All right. So a couple of things to, I want to go through and let's talk about the midterm for a few minutes. And then I'm going to, we're kind of transitioning towards interprocess communication and file stuff. We've talked about file locking at the high level. We're going to do a little example of that probably today into Monday, but we'll see what goes down. Let's see. So midterm will be, what's Wednesday, 17th? So 3/17. Blackboard during class time. It's the usual 10 questions. Designed to take about 30 minutes. You will have the entire class time to do it. I will be live on Slack during class in case there are questions. Otherwise, submit any assumptions you made with your answer. Close book, close note, close neighbor. There will be at least one conversion question as usual. So either, convert some number from like binary to hexadecimal or something like that, or it could be a speed or a size. So it could be, how many kilobytes is 227 gigabits or something like that. So be able to know all those different data sizes, the bits to bytes, and the scalar of 1024 as you move up and down the columns. So that'll always be on my exams. You always have at least one of those. So this first exam is going to probably have more code to read than code to write, although there'll probably be at least one C programming question on there. So I'm going to go back through the slides here and kind of point out the things that are worth looking at. And then, any questions you have, we can talk about. Otherwise, look at that stuff over the weekend and come to class with any questions on Monday, and I'll review those before we keep going with the example we're going to start today. But let me at least just start off at the beginning and see what's going to be important on this exam. All right, so, I don't know what format this is going to come in, but, understand the difference between a distribution and a kernel. I don't know if I'll ask that question specifically like that, but at the very least, the word kernel is probably going to appear on this exam several times. So when I reference the kernel, you should know that we're talking about the actual operating system. And fast forwarding a little bit, that the difference between kernel space and user space is an important thing. Oh, there's Noah, you're late. We were just talking about you. Well, am I gonna have to fight this guy?
Maybe.
Oh, okay.
You just can't get him to drink. I have stories.
Can't get him to drink. He gets aggressive when he drinks.
Yes.
And he's so Sambo is a martial art, right?
Yeah, Sambo.
Sambo.
It's like if
Is it one of the killing ones?
What?
Is it one of the killing ones, or is it like a?
It's like if jujitsu got 100 times more intense and people died during it.
Oh, okay. Well, that sounds fun.
Yeah, and he does combat sambo too, which is like where you punch. So it's basically MMA without the cage, and you can headbutt.
Ah, so combat sambo.
Yeah.
Okay.
Yeah, and he's the U.S. national champion.
Oh, well, that sounds fun.
Yeah. And
So
the
do you think
Johnson
I
State-
should challenge him, or is he going to challenge me?
I think you should probably challenge him.
That's what I'm thinking.
Be bold.
Have your camera running. All right. So definitely understand that concept of kernel space versus user space. I'm probably not going to ask questions about history of our distributions and things like that we talked about. But you know, that word kernel is an important aspect that we've dealt with quite a bit. Certainly understand the concept of compiling, how we're targeting an architecture as well as a operating system. That is kind of extra important for us since we're specifically using operating system things, specifically like in Linux for working with their modules and things like that. But understand the core component of compiling, converting from a high level language into a low level language. For us, we've been compiling down to an i386 Intel-based language. Not that big a deal since we're not operating at the assembly language level here, but the operating system we've been working with is Linux. So we're at the mercy of the system calls that are available to Linux, and that's what all our examples have been using. I probably won't ask about like what a driver is, because you know, things we've talked about so far in here has been more about leading up to this idea of inter-process communication. But maybe if we were to say the theme of the first 8 weeks had to do with mechanisms for moving between user space and kernel space. How do we run software at the kernel level with certain permissions? And then certainly more recently, when we looked at 2 specific system calls for actually getting information between the 2, kernel space and user space. But how does a user ultimately write a piece of software that runs in kernel space? All right. Concept of a microkernel would be fair, because that was effectively the gateway drug that got us to this idea of kernel modules and drivers. You know, the idea that the microkernel is a completely, you know, stripped down version of the core operating system with kind of features that lay on top of it, like the module subsystem and things like that, being add-ons that the user can kind of plug things into. I don't know what form that might come in there, but you know, if I ask the question of, you know, what's the difference between a microkernel and a traditional, I would probably flag it as like monolithic kernel. You know, we'd be talking about the idea that we're pulling a lot of the stuff hard-coded into the operating system out and turning them into modules. The example we would have used early on would have been probably like an older Unix operating system where I maybe pointed out that, you know, all the hardware it would have ever supported had to be built in, compiled into the kernel day one. And then what you're stuck with is you're at the mercy of, you know, all that hardware is the only thing that'll work with that operating system. So when a company comes out with a new piece of hardware later on, it's not going to work until you recompile the whole kernel. We're moving to a microkernel setup with a module subsystem that supports drivers and things like that. Now you can have a company come out with a piece of hardware along with a piece of software that knows how to talk to the kernel through, or talk to the microkernel through like the module or the driver subsystem to tell it how to use that piece of software. Or I'm sorry, that piece of hardware. Go ahead.
So when you said pulling hard-coded stuff out and turning that into modules, is that monolithic?
The monolithic thing would be the like the older kernel style where everything was in the kernel, including all the drivers and things like that, and it wasn't changeable.
So we wouldn't say that had modules.
Correct. Yeah. Well, yeah, the monolithic kernels would have been very old school before modules. Microkernels came about with the idea of hey, you know what? We might have new hardware that comes out in the meantime, between the next time we release the update to this operating system. So it might make sense for us to give some way for companies to allow you to use their new hardware on your operating system. And the mechanism for doing that came by saying, we're going to actually have the core operating system, the part that doesn't get recompiled very often, only have the absolute necessities in it. That way we can have these other things that, you know, it does create some new problems, like, like we've been talking about the security issues between the kernel space and the user space, and what roles these, what permissions folks have, and how do you have programs communicate between those. So it does create some new problems, but it also solves the problem of an operating system doesn't have to support every piece of hardware it was ever going to support day one. In fact, we can even say that an operating system with a microkernel barely has to support any hardware inside the microkernel. Maybe the things that would be built in are going to be, and they're probably built in as modules now, but are going to be like generic VGA driver might come with the system. So, hey, I can show stuff on your screen. If you want to utilize some kind of fancy schmancy NVIDIA GPU or something like that, well, then you better install a module that teaches me how to talk to that guy above and beyond just showing pictures on the screen, that type of stuff. Okay, certainly this concept, when we're kind of talking about, because we're really talking about software at the operating system level, and there's almost a chicken or the egg type situation where we use the programming language like C to write the Linux operating system, for example. Well, we've talked about compiling targets an architecture, right? And also targets an operating system. Well, if compiling the code that we were using to write the Linux operating system needed to target an operating system, what operating system were we targeting if we were in the middle of writing an operating system? Okay, and that's the BIOS. So when you first turn on your computer and something happens, even if you're, you don't even have a hard drive installed, so like maybe in your 175 class when you built computers, even if you didn't plug a hard drive in, some stuff showed up on the screen, right? Maybe it's counting. You don't actually see this much anymore, but they used to count the RAM. You see that on the screen, stuff like that. Then something would usually pop up, for the BIOS, and press delete or press F8 or something like that to get into it. That's actually kind of this basic IO system, the BIOS, which is a very simple operating system, but an operating system nonetheless. All right, so if you have different types of BIOSes, which more recently BIOSes have been moving towards kind of a new standard, which is okay, but when you're writing operating systems, they are running on top of that BIOS. So when you compile, it's something called bootstrapping, where you can where there's a handoff between the BIOS to the loader for the new operating system, whether it's Linux or Windows, whatever. Linux, one of the main loaders is something called grub. So it's a program that the BIOS ultimately launches. They put it into the very first sector of the hard drive, because that's where your traditional BIOS will look. Like, okay, when I go to launch the real OS that the user is expecting, where do I start? So we can kind of think of the operating system start button as kind of being in that first sector, or maybe in a very specific sector of the hard drive, depending on the architecture you're working with. But that's what kind of gets that ball rolling. So for Linux, it goes from the BIOS to grub, and then grub ultimately hooks it into whichever of your partitions on your physical hard drive that the operating system was installed on. And you've seen this if you've installed Windows before. It'll ask you, if you have two hard drives in your computer, which hard drive do you want to install this on? Something like that. The C drive or the D drive, something like that. Which actually had kind of gone out of vogue for a while, right? A little bit older computers, it was pretty common for there to be two hard drives in the machine. Because you added a second hard drive for more storage space and things like that. But then what happened is our hard drives became more and more reliable, and they also became much, much bigger for not that much money. You can get a 3 terabyte hard drive for your computer for under $100 bucks. But now So it was pretty common then to have computers with one hard drive in them, but now it's becoming more common again for computers to have two hard drives in them. Why? Why have we kind of gone back to the two hard drive model when you buy a new, specifically if we're talking about gaming computers?
I only thought that you could have a solid state like operating system and a hard drive because that could hold more.
Yeah, that's it. And it's less necessary today because solid state drives have come down in price for higher capacity. But generally speaking, we can take like one of our, like the Omen machines that actually, no, this isn't one of them, but we had one in here. But one of our Omen, HP Omen machines, where that machine shipped with a 32 gigabyte solid state drive. And then it had a, I don't remember if it's a 1 or a 2 terabyte mechanical hard drive in it. Well, that 1 or 2 terabyte hard drive, it's like a $40 hard drive. It's not an expensive hard drive, but it can hold a lot of stuff, right? And if you're buying this as a gaming computer, games are, they're big. You download a game off Steam or something like that, it's a 50 gig download or whatever. So having that huge capacity might be nice, but you also probably want your computer to boot up relatively quickly, right? If launching your game initially takes a little bit longer, that's not the end of the world. As long as once the game is launched, it feels quick, and that's going to have more to do with performance memory and stuff like that. So you want to have 16, 32 gigs of RAM, but you know, the overclocked stuff with the heat sinks on the RAM, that looks really cool. And a lot of times there's colors, sometimes there's lights. You've seen that, the gaming light RAM. Oh, that's the stuff. It's true. Yeah. People spend money on this. And the liquid cooling stuff.
Like that one computer I showed you. That was made to look like a whiskey barrel.
I'm not remembering that.
It's pretty cool if you look it up. It's like the actual like case is made out of a like whiskey barrel.
Okay.
And then it's liquid cooled.
With whiskey?
Well, and there's a big pipe in there.
Okay.
And that goes to a whiskey bottle, so it looks like whiskey.
Ah, I see.
Because they like dyed the water. It's super cool.
Oh, okay. Well, that sounds at least kind of neat. I mean, like in a geeky way, right?
Yeah. Like,
you know, for like 5 minutes, like, oh, and then you realize like, okay, how much money and time did you waste doing this? Yeah, but in any case, certainly understand this concept of compiling the target architecture being like the processor, things like that, and then the target operating system kind of meaning some different things. I'm probably not going to, like, you know, we just had that little discussion about like, you know, hard drives and things like that. I'm not going to ask stuff about that. We want to, you know, even though we've covered kind of a lot of topics in the course and gone off in the tangents as I do, but, you know, when I'm writing the exam, I'm going to be writing it through the filter of the topic of this class is systems programming. So we're going to be focusing more on the programming aspects than the, you know, important building blocks that got us to where we are today. And it's not that those are unimportant, and especially on this first exam, we've done a little programming leading up to this point. We've looked at a lot of code in the first 8 weeks, but we've done fairly limited amount of actual programming ourselves the first 8 weeks. We're going to be doing more programming the second 8 weeks. Now that we have kind of the cursory material, and now we sort of we're moving towards being able to write software that we have like legitimate examples for. So there'll probably be more actual coding on the final than on the midterm. The midterm will be more of reading code and then connecting the most important dots relative to kind of our evolution of our operating systems and stuff. So not so much, you know, like which Windows distribution came out fourth. You know, I'm not going to ask you something like that, but that idea of a microkernel, super important. The idea of how compilers work, and when we're targeting an architecture and targeting an operating system, what does that ultimately mean? That kind of stuff. Those would be fair game for questions, but not some weird trivia knowledge that I'm not claiming is unimportant. It's more just, you can always look it up, you know, if you needed to. Go ahead.
So will you be asking more like what functions do, or more like
Well, I mean, that would probably depend. I probably won't ask detailed stuff on like what a function does. I might give you some code and say, write 2 or 3 sentences that explain what's happening here, or something like that, kind of proving that you can read the code. Because one of the things that, hopefully is becoming less and less intimidating is when you're looking at, first of all, C code, which can feel a little bit intimidating with some of the syntax stuff, but specifically systems code in C, where, we're not as, coming from a Java, a C# or a Python background, we're not used to that cadence of passing in a pointer to a buffer that ultimately gets filled up with something. And so I'll be testing more. Do you understand what's going on in this code? Because it is a different approach to programming than most of us are used to, right? But I probably wouldn't ask some sort of, deep question about, some function that, we've talked about like a general use for it, but the function can do 15 other things and it takes in 11 parameters or something like that. We use 2 of them, right? I'm not going to ask you about some random parameter number 7 that, you have to go to a man page to find out what that flag was for or something. So it'll be fairly straightforward, very indicative of kind of the stuff we've done in class, walking through code. I might have you write something very simple in C, maybe something with pointers or something, just to make sure your mind's wrapped around kind of the pointer syntax. But I would think there'd be more actual programming on the final. Okay. Something with Makefiles could be on there. These are an important concept when it comes to any sort of OS programming. This idea that when we're having to bring together source code that we wrote, plus stuff that's libraries that are part of the C library, plus stuff that are core components of the operating system, which we've had to bring into our code. This is a new approach for most of us, right? We typically, when we've written software previously, we've been writing, kind of consumer level software, business applications, things like that are fairly self-contained, not overly, especially with Java, right? But not overly reliant on a very specific version of an operating system or a Linux library or an ASM library or something like that. So this idea of a Makefile, comes into play where it's compiling this code isn't as easy as just hitting a play button like we were kind of used to in the past with like clips and things like that. I kind of have to bring lots of things in, and I'm linking certain libraries in at compile time. And that's something that, when you first have to figure out how do I compile this program can be a little bit daunting. But once you have that, pulling it into a Makefile for kind of managing your directory allows you to do things like, building, and ultimately, I don't think we've actually done this, but I wrote some scripts that do it, but it's not uncommon for, if you download an application, the source code application for something in like Linux, we've looked at maybe installing things using apt-get. I think I've probably used apt-get a couple times in here for installing a package. So that's kind of the cool kid, more modern way of downloading a pre-compiled package for an operating system and installing it. But if you go more old school, there's something called Tarballs, .tar.gz files. Sometimes the upgrade to that was a .tgz file, but you have to effectively unzip it and then untar it. Tarring is a tape archive. And what you'll end up with is a directory that has code in it that you then have to configure and build. So a lot of times your cadence for doing that would be like going into that directory and doing a /configure, which is a little program that asks you all these questions. Do you want to support this? Do you want to support that? Do you want to do this? Do you want to do that? So you're answering a bunch of yes, no's, and that kind of sets it up, and then you do a make build, and then a make install. That last part of the make install takes the executables that it's built and it copies them into maybe it's the /bin directory or the user bin directory, something like that. All right. So at its core, this idea of a Makefile simplifies the compiling and potentially even the installing process of an application, because when we're dealing with applications at this level, not our little rinky-dink business applications, but bigger things, bigger programs, or in this case, drivers or whatever, which are effectively just programs, we might want to kind of figure out the way of building it once and then have it inside this thing so we can use it. So I won't be, there might be kind of a generic question like, what is a Makefile? Maybe I would show you a Makefile and kind of ask you to, explain some aspect of it or something like that. Although I'm thinking I probably wouldn't do that because we haven't done fancy stuff with Makefiles. We just said, hey, here's a convenient way of building our code and also a convenient way of cleaning up our directory, of kind of unbuilding it. So I probably wouldn't show you a Makefile, ask you anything about it, but you should know what Makefiles are and how they might be used. So this is kind of a governing thing of almost everything we've talked about up to this point. And we have this idea of our normal system memory, and then more recently we've kind of talked about how memory is mapped differently for kernel space versus user space. And that's where we have those two functions, and we'll bump into them here in a little bit, those two functions that allow you to copy stuff from the user into the kernel and from the kernel back into the user, and it's going to do that mapping for us. So all this stuff lives on top of our normal system memory, our 16 gigs of RAM, that thing in our computer. And then the operating system then effectively manages that memory. And one of the things a modern operating system does is it divides it into kernel space and user space that we've seen is mapped differently through those couple of functions, whatever. But the point is that these two spaces are for different purposes and follow different guidelines, have different security rules associated with them. All right, so then we have our microkernel. So this is the thing with everything, all the extra stuff pulled out of it. So it's only the core operating system concepts, process management, memory management, things like that, with stuff like drivers and things like that pulled out into a module subsystem that allows you to create modules for generating stuff. And these guys all share this global namespace. So when we install a module using insmod, we have to be careful with the names of the modules as well as names of global static variables in those modules, because those names have to be unique among all the modules that are running in that module subspace. All right. So that's what this whole naming conflict thing is. All right, so as it comes to modules, this connection thing here, where you can write methods that are named whatever you want, but then ultimately we use the module init and the module exit system calls to let the module subsystem know that this function is the function you should call when you initialize this module. This function is the function you should call when you exit this module, uninstall the module. Okay, so understand that relationship. We kind of connected it to like interfaces in Java. I really won't ask anything about character devices versus block devices, because since we haven't had concrete, like, great examples of this, because we're kind of writing fakey drivers, fakey things like that. I mean, a block device is like a hard drive. A character device would be like a fake hard drive. It's a file that is either used for reading something, or we can write something to it for sending information between 2 points. But from our perspective, we aren't making a real designation between what's behind the file. We've talked about that in a POSIX-based operating system like Linux, everything is a file. So character devices, block devices, it's all the same. Our interface to them is through a file, and we have a very kind of cursory understanding of most of it has been reading from a file. There's some program behind it that when I ask for something, it delivers what I asked for, you know. And whether that's reading something from a hard drive somewhere with a much more complicated program than we've written, or it's spitting out hello world, doesn't matter. It all happened through the reading process of a file or writing to a file. Same thing with these major and minor device numbers. You know, I'm not going to ask specific questions about that, but just every module has a unique identifier. You know, there's a social security number, you can think of it as a phone number, an IP address, whatever. It has a unique way of representing itself in the system. And that's how the operating system keeps track of it, because operating systems, computers like numbers, human beings like words. Okay. So like what I was saying here, I probably won't ask you anything from this slide, character versus block devices, because we didn't have concrete examples of how to truly differentiate them in terms of our use cases. You wouldn't have to memorize anything. I mean, size of a char, it should be pretty straightforward for us. It's always been a byte, but you should be comfortable enough with memory and sizes and things like that, where if I did ask a question, showed you some code or something where we're allocating some memory for, you know, 50 integers, and I say the size of an integer is 4 bytes, and I asked you how much total memory was allocated, you should be capable of doing that math. Academically, understand what structs are. Again, we haven't written a lot of stuff with structs, so there won't be a coding question dealing with structs, at least on the midterm. We'll be using them more between now and the final. In terms of actually writing them ourselves. We've seen plenty of them up to this point, but we haven't written them. But understand that concept that the purpose of a struct, kind of the precursor to a class, to an object. It holds a bunch of name value pairs, but doesn't necessarily have functions in it. But we've already kind of seen this idea of callback functions like we saw right here, where we can pass the name of a function. This is effectively a pointer to this function into this system call. All right, and so inside of this module init system call, if we were to look at that source code, this guy would be the kind of a weird void pointer thing, and in language theory, we would call that a closure. So it's taking in a pointer to a function as a parameter, so it knows where to send parameters to when it actually gets them. This could be kind of important. This is something we talked about quite a bit, and it's an important computer science concept, the difference between a struct and a class from a pass by value versus pass by address perspective. Structs are passed by value by default. Classes are passed by address by default. The whole class side of this isn't really important in this course, because we're not dealing with an object-oriented language, but we're dealing with a lot of structs, and we see when a struct needs to change inside of a function, we're passing the address of that struct. We're expecting a struct pointer, and we're making changes to that struct with the expectation that we're changing it in memory, but we had to use C's syntax for requesting the address and sending the address of a struct, because if we didn't send the address, the struct would be passed in by value, and therefore any changes we made to the struct inside of that function would not stick. Certainly be comfortable with pointers, the whole pointer syntax stuff, be able to read code that uses pointers, be able to write simple code that uses pointers, because I mean, keep in mind, and any programming questions I might ask, I'm not necessarily holding you to a perfect C standard, you know, since I'm presuming you're not going to be compiling stuff when you're writing your class or writing the code, but you know, most of you have had, well, all of you in here should have had at least CSC450, so you should have effectively 3 semesters of computer programming background. So if I ask you to solve something using C as the language, you know, you should be able to give me a relatively competent shot at it, even if it's not necessarily a module example or something like that. Okay. This is more about pointers, understand the difference between, you know, the value that A holds here, which is a int literal, versus the value that AR holds here, which is a memory address, where enough memory for 5 of these guys lives in contiguous memory. Know what contiguous memory is? What's contiguous memory? Memory in a row, right next to each other. I wouldn't ask a question about this. We did recently start talking about, actually, we've talked about masking in here, but I think only as an example from one of the things. We didn't like go into it. We just were looking at code and saw that what it was passing in was 2 or 3 macros, bitwise ordered together, if I kind of remember. And I referenced that as being a masking thing. So possibly on the final, we'll actually do the math for that. Not that it's necessarily hard, but again, we don't have context yet for why you might do that. But so forget about this slide, but at least academically remember that the double vertical bar in C-based languages is the logical OR operator. The single vertical bar is the bitwise OR operator. So it's working with numbers at the bit level. Oh yeah, there was our masking thing. Maybe some high-level stuff in interprocess communication. We've referenced semaphores quite a few times, talking about it kind of like a bouncer. So we really haven't written stuff with semaphores yet, but the idea of protecting a resource, I probably use kind of like a McDonald's cash register example or something, where you have a single register like a cash register, or you have a single resource like a cash register, and you might use a semaphore to control the number of people that can reach that register, or the number of programs that can get to that register at once. You know, the idea of semaphores goes hand in hand with the idea of atomic operations, operations that happen as if it's a single instruction. So that's another theory thing that would be important and fair game on the exam, this idea of atomic operations and how those are difficult. And it's up to the operating system to kind of fake that for us. And that's why these interprocess communication, these system calls, having the ability to run in kernel space and kind of take over the process manager or the CPU manager and say, okay, the next thing that's happening is happening kind of in protected mode, because it's going to happen as if it was atomic. I don't care how many assembly instructions had to happen in order for this to happen, but I'm locking down the CPU so that there's a guarantee that the next thing that gets sent in here, the next 6 instructions that get sent in here, are not interruptible. Something like that. So semaphores are reliant on that to avoid race conditions. Go ahead.
Atomic operations are separate processes that are running at the same time.
No, atomic operations would be a in the ideal world, we would say an atomic operation is a single instruction of assembly code that takes exactly 1 CPU cycle to execute. That would be the ideal world. Because if it takes exactly 1, you can't subdivide a single CPU cycle. So if it takes exactly 1 CPU cycle naturally, that would be a, let's call it a pure atomic operation. But we're going to say that a lot of things are more complex than that inside the CPU. So it actually might take more than 1 CPU cycle to execute that instruction, or maybe the collection of instructions. So we can say that that instruction is still atomic if it happens as if it occurred in a single CPU cycle, of ultimately talking about that it can't be interrupted. Some other process couldn't have come in, you know, half the way through and made some modifications. Once the instruction starts, it has to finish without any interruption. And then we can say it happens as if it's atomic. And that's a really important concept when it comes to interprocess communication, because we are reliant on things happening as if they're atomic, with like the semaphore. You know, in the real life example of that is that we have that bouncer guarding the McDonald's register at lunchtime, and 4 of us are all running in there at the same time. You know, we might need to go to the tape to find out who got there first, right? like horse racing or Olympic, Olympic running or something, see who actually won, right? And the idea is that at that operating system level, if if things are not happening atomically, I think we had that code example where I said this was kind of like fakesy or ghetto semaphore or something like that, where it's like, look, this technically isn't atomic, but we're just going to kind of hope for the best type thing, and probably wouldn't be a problem. We wouldn't, if we're talking about like Olympic racing, we wouldn't need atomic operations if it was me versus Usain Bolt, right? The human eye will be able to detect the winner of that race, right? Okay. Similar with the Sambo fight tonight. Yeah, I think you should save your money, probably. Okay, he's probably fast with me too, so running away is not even going to help. Okay, but if we're talking about things that are happening at the operating system level, things that are happening on computers, and they're happening really, 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 really fast, this concept of a race condition, or hey, it's too close to call, who tried to grab the resource first, that becomes a more and more real thing, the number of things that are competing for the same resource, and that, things that are happening in microseconds on a computer, then it becomes a real deal. And it becomes more and more important depending on the nature of the software we're writing. So the second 8 weeks here, we're going to be exploring actual interprocess communication examples where it might, like we even started looking at lock files and stuff last time, where, it might be bad if we tell two different processes that they're both allowed to write to this file at the same time. We might end up with a resulting file that isn't the intended resulting file. If whoever wrote last is going to be the one who wrote the truth, something like that. So there are real examples of things where it does matter that we don't let more than one thing get at a resource at the same time. If you're just reading from a resource, we can maybe say, look, we don't want two people to try to order or try to read the menu at McDonald's at the same time. That way we have a little bit of order in the line or something, but it's not the end of the world. So sometimes it's more, we're doing it out of, organization as opposed to a necessity, but some things are important. All right. We haven't really talked about this yet because we talked about file locking, but we kind of glossed over this idea of what is a sequence file. We did look at code using sequence files, and it's actually not really important what they are. A file is a file. Everything in Linux is a file. Similarly, I might ask something about, it would be a high level thing about the proc file system, like what its purpose is. The proc file system is a directory that has files that relate to the running processes on the system. We did talk some about the idea that we also have a more modern sys file system, because the proc file system kind of got overused in the past. We're like, hey, we didn't know where to put this other thing, so we just threw it in /proc. It's an organizational thing. A file is a file is a file. All right, so where we're putting them is more kind of like, where do you expect the stuff to be in Linux? It's easy to overthink that and get, if you go to the root directory, the / directory, and you look in there and you wonder what what's inside the user directory, what's inside the etc directory, what's inside of bin, all those things. There's kind of intended things, but they're just directories, right? And there's kind of like an expected organization, but there's no hard and fast rules. Hey, I'm looking for a pair of socks at my house. Where do I find those? Well, probably in the sock drawer, but maybe not, right? Maybe you keep them in your junk drawer or something like that. It's allowed, it's just unconventional. So if I talk about the proc file system, the idea would be like, this is the file system you might write code to talk to if you're trying to communicate to a process, or potentially, as we're starting to get to, between running processes. Okay, so these are those two functions I referenced a couple times earlier, where we have these and we actually are using the ones from the Linux U-Access thing for Ubuntu, but it doesn't matter. We have two functions that allow you to copy to the user and copy from the user. Why do we need these? And the punchline there is that memory is managed differently, and memory addresses are not one-to-one, are not the same in kernel space as they are in user space, even though they're both sharing the same physical memory locations. Just our way of talking about those memory locations is different. Because what's a memory address? A memory address is just a number, right? We're talking about a place in physical system memory. But ultimately, when we say go to this memory address, we're talking to the computer who's going to ultimately talk to the bus that talks to system memory and say, go to a certain physical place in memory that has the information I'm asking for. The memory address that the person put in might not necessarily directly correlate to a physical location. It might correlate to like a kind of a fake, a mapped location that we then need to translate into the real address so we can get to the actual place in physical memory, something like that. So for us, understanding that kernel memory and user space memory aren't necessarily they reside in the same physical hardware, but they're not necessarily mapped identically to each other. So they're not compatible with each other without using functions like this that allow you to move things between those two systems. Okay, I think that pretty much gets us to where we're at. We did look at the difference between a pipe and a socket, so that would be a fair game as we're just starting to get into inter-process communication. Otherwise, I might have like a single code example and ask you some questions about that code. What's happening in this function, or what does this line of code do? Something like that, kind of proving that you can read that code and aren't just sitting there going through the motions when we're walking through it in class. All right, that makes sense? So take a look at some of our code on the GitHub repository over the weekend. Make sure that you feel like you can kind of maybe explain to somebody else what that code's doing. And if you find that there's some hiccups in there, ask about it in class on Monday and we'll go over it. Otherwise, on Monday, what we're going to start doing is we're going to create a file IO program doing something with what's called ROT13. It's the old Caesar cipher, because we're going to try to fake some inter-process communication by sending encoded messages through a couple of our different things here: shared files, shared memory, maybe sending through pipes, that kind of stuff. All right, questions, comments, concerns, bribes? Go ahead. Yeah, it's you don't see the grade already?
I checked this morning. I wasn't there.
250 had the same problem. I'll look, I have a meeting right here after class, but if you don't see it released by, because there's a button I have to hit to release. So if you don't see it by, say, 5 p.m. today, message me or something, but I'll get it fixed. Something's not right there. So I apologize. But yes, everything should be graded. From my perspective, everything's graded. All right, I will see everybody on Monday. And remember, the exam is actually on Wednesday. So we'll have normal class on Monday where I'll take questions if you want to do them.
Are we doing the exam in person, or is it going to be?
It's on Blackboard, and so we won't meet in class, but I'll be live on Slack if you have questions during it.
And how long do we have to complete the exam?
I mean, I'll design it to be like 30 minutes. I'll probably put a little bit wiggle room on either end,
Okay.
but it should not be a time crunch
Okay.
issue. I would plan on an hour, a class time,
Okay.
to do it.